Okay, continuing on with, now we have our data, and not only do we have our data, but we kind of fixed everything so that we got the exact amounts of each one. So make sure in your notes right now that you mark off those three. When we talk about pressure and volume and temperature of this sample of gas, we got everything fixed to how we can use it now in our calculation. Okay, so we're going to give you some really good hints that will help you in doing tomorrow's lab, because you're going to have a similar set of data by the time you're done doing the lab, or that data will be provided for you if you're a distance learner. So method number one is referred to as the combined gas law method. Okay, so when I say on the lab report, method one, what's the molar mass, or the atomic weight of the thing, you're going to use this method. All right, so method number one, using the combined gas law to figure this out. Well, we did a lot of work already for this. We did P1 V1 over T1. And what we're going to do is we're going to convert this into STP, because there is a time when you know the temperature and the pressure of a gas at standard temperature and pressure. You know the volume should be 22.4. Of course, ours won't be that, but we can set up a little ratio. So let's convert into STP. So these numbers are the ones that you just boxed in, and I'm going to do this a couple times here. Just go back, yep, 962,753,296. So nothing new there. Those are our initial conditions. And then this was, remember, was in atmospheres. So 1.00 is standard pressure, 273 standard temperature, and then we're going to solve for the V2. I would continue practicing these so that it's my experience, even when I teach second and third year chemistry to people, you're still making a lot of silly mistakes on the math here. Just cross multiply those guys, divide by the other diagonal, and you should get 6.68. Of course, this has 3 sig figs written all over it. So that is your new volume. So at standard conditions, standard temperature and pressure, our sample would occupy that volume. Now, how can we use that? Well, we can use that this way. Like I said, you know that 1 mole equals 22.4 liters for any gas at STP. X moles for 6.68 liters. You can see we have just a little fraction of a mole, maybe just his head, just a little cute little head. All right, so we're not going to have an entire mole. Cross multiply, solve for X, you get 0.298 moles, about a third of a mole. Okay, so we now have enough to do the molar mass of the gas, because molar mass equals grams over moles. And grams, we already did that, didn't we? We weighed it before and after, and it was 4.78 grams. Make sure you know where we got that. Remember those nice little drawings you did and you subtracted them? That's how you're going to get your mass. When we do the lab tomorrow, or the simulated lab, you'll get that mass from the lighter. We're going to weigh the lighter before, and we'll weigh it after. The difference will be the mass of the butane. Now this one, we don't know what it is, but when we divide them out, we see that you get 16.0 grams per mole. That's starting to be a really good case for methane. CH4, right? 12 plus the 4 hydrogens, 16. Probably methane that is in our Bunsen burners in class. All right? So, we're not going to stop there, though. I'm going to show you that there are 2 more gas laws that will sort of introduce one today just because of the hybrid thing. We have to do it in this order. Normally, I'd probably introduce these laws and then do the lab, but that timing just didn't work out on that with the Wednesday thing. And so we're going to introduce this gas law here today, and it's called the ideal gas law. PV equals nRT, nicknamed pervert inert. Okay? And the ideal gas law, or pervert inert, is something that has 3 things that you already know what they are: pressure, volume, temperature. And then we got the NR, N and R. What do those represent? Well, the moles equal N. So to figure out the number of moles, which is something that we did with the other method, we wanted the number of moles, so we could go grams to moles. So that's why we want to solve for N here. So notice what I did is PV, and I took that NR and just dropped them down on the bottom. So N equals PV over RT. Well, we have PV and T, don't we? Well, let's add those in, because those are the same ones. I won't go all the way back to it this time, but the ones you boxed in, the ones we corrected and fixed, that was the pressure and the volume and the temperature of our gas sample. Now, R is a constant, okay? So make sure you note that. Now, a constant isn't going to change as long as this is atmospheres, which it's not always going to be. This is liters, which it's always going to be, and that's Kelvin. So the times it varies, and we'll see this with our lecture on Wednesday. Your pressure units could vary, and if your pressure units could vary, then R changes. But otherwise, if this is atmospheres, liters, and Kelvin, no matter what the other numbers are, this is a constant. In AP chemistry, they have that number memorized because they use it very often. And this seems to be a pretty common one to go to atmospheres. All right? So look at what happened. When you did that, you get 0.298 moles. And if we go grams per mole, the gram's still the same, divide that out, you get the same answer using 2 different methods. So this gas constant is a pretty robust way for solving these gas law problems, because the other thing that it takes into account that the combined gas law did not is the amount of the gas. Because we had pressure, volume, and temperature, but we never really talked about the amount. So really, the only thing that pervert inert adds is the amount of the gas. And what a constant is a scientist's way of cheating. Yeah, that's right. Because PV didn't equal NT, so they said, well, how about if we put that number in there? Then they'll equal each other. That's what a lot of these physicists do that all the time. Don't tell Lizzie I said that. Okay? So, we still got 16.0 grams per mole. And, you guessed it, there is a method 3. Okay? So, what's going to be really interesting about this method is it's going to be another equation that we kind of worked with, but it's a different version of that. But you're still going to get the same answer, which is 16.0, which is probably methane. So here's the equation. MM equals dRT over P. Probably could figure out what MM stands for, your molar mass, and D actually equals density. Okay? So the molar mass can be defined as density, which is mass divided by volume. We have a mass, we have a volume, so we have a density. Piece of cake. Just like the lab we did with the Red Wing shoe stuff. Just density equals mass over volume, 0.635 grams per liter. And if you really want to be impressive, we know what the temperature is, so you can write the temperature with the density. Might be one of those little bonus things for doing a really good job on the lab. So we do know for this density calculation what the temperature is. So then you plug in here. R is a constant, right? So it's going to be the same thing as it was when we did PV equals nRT, or method 2. So MM equals 0.635 grams per liter, which is what you want for the units. You get to leave those out in the gas laws. Constant, it's not going to change. It's going to be the same constant as it was way back there, which is 0.0821. Boom. And the temperature, same. Pressure, same. And unbelievably, even though you use these two different numbers, you threw in this one, boom, 16.0 grams per mole. So you can see this and method 2 and method 3 went right to getting the molar mass. And this one's designed to do that. So I want you in the lab, you're going to have to show me that you know how to do all three methods with your data. Okay? So that's going to be really important in setting up this lab. Okay? So that will provide the skills you need. There's one more thing about the chemical reaction, which you're going to have to maybe research a little bit. But in this case, we would speculate that the molar gas, that the molar mass of that unknown gas being 16 is probably methane. And you can even do the circle square method, and you're like, wow, those numbers worked out perfect. Almost like someone planned it that way. Okay? So that's our conclusion. When we get to the very end, with your lab, it's going to be 12 carbons, 48 plus 10 hydrogens. That's another 10 on there. Should be theoretically 58 grams per mole. So let's see if we can do that with a butane lighter in the lab tomorrow. Okay, so and again, all distance learners, even Thursday, Friday cohort, you will be provided the data for the lab, and you will get to use the period to do the calculations. Okay, so you miss out on doing the lab, but you get the advantage of having more class time to crunch the numbers. Okay, all right, so that is the pre-lab, which we will go ahead and do that lab tomorrow. Thanks for coming, and this is the end of Prelab Lecture number 2.